Hello, everyone, and welcome to today's session, REV7 Deep Dive. Thank you for joining us. Today's webinar will be presented by Ouster's very own Tom Gray, Director of Product Marketing. We will be doing a live Q&A after the session, so please feel free to submit any questions during the presentation. As a reminder, this session will be recorded, and a copy of the recording will be sent to you once complete. Thank you again for joining us today. Please welcome your presenter, Tom Gray.
Awesome. Thank you, Stephen. Hey, everybody. Thank you for joining. We're excited to give you a webinar giving a little bit more technical detail on our new REV7 sensors. I'm going to be walking through a little bit of a technical Tuesday. I'm going to be walking through some LiDAR, basically how LiDAR works, a walkthrough of signal to noise ratio, and some detail on our new chip and how it works. I imagine there may be some questions, so please feel free. If you can put questions in the chat, we're gonna aggregate them. I'll probably be looking over for a minute at my other screen where we're logging the questions, and then we're gonna answer them at the end. So, but please punch them in as you have questions. Just know we'll get to them at the end of the presentation. All right, let's get into it. So I know we had a short webinar right when we launched the sensors. It was a little crazy over here getting everything out the door for the launch. And so, we gave just kind of a quick overview of how the sensors performed. But today we want to do a bit of a deeper explanation so that you can understand not just, what the new sensors, the REV7 sensors can do, but why they are capable. I mean, they doubled the range, improved the precision, improved dark object detection, really dramatic performance improvements. And I want to make sure that everybody joining here can walk away and know what the sensors are, but more importantly, know how they achieved those gains and why those gains happened. So a quick recap or a quick overview for anybody who's joining for the first time. Back in October, we announced our new REV7 sensors. They're our new generation of LiDAR sensors. They come in 4 different types. From left to right, we have an OS dome, the OS0, the OS1, and the OS2. Now, all of these sensors are based on our digital LiDAR architecture, so they have common componentry inside. But what we do is we customize these sensors based on field of view and range. So the dome, as you can see with kind of that dome black window, is a hemispherical field of view and sees about 20 meters. The OS0, the second from the left, is a short range sensor. It has a 90-degree vertical field of view out of that window and sees about 35 meters. The OS1 is our mid-range sensor. It has a 45-degree field of view and sees 90 meters. These are all on 10% targets, by the way. So the range on brighter targets will be about double what I'm saying here. And finally, on the right, the OS2, which has a 22.5-degree field of view and sees about 200 meters at 10%. So today, just summarizing, we're going to talk about how we upgraded our REV7 sensors with our new L3 chip. That's a new semiconductor. It's the core piece that powers all of our sensors. We're going to talk a lot more about that in just a minute. We're going to talk about the significant range, precision, and detection improvements. I've got a lot of content. I will go through it. I mean, I'll go through the slides fairly quickly, but just a lot of demonstrations and visuals showing the performance of REV7, also some comparisons to our prior version, so you can understand practically what I'm talking about when I talk about the chip improvement and what that did for our sensors. We're going to talk briefly about the upgraded internals. The REV7 sensors, the performance of the LiDAR sensor, like the point cloud performance, improved dramatically. That wasn't the only thing that improved with REV7. We also improved the hardware. So we'll talk a little bit about its improvements in like reliability that come with these sensors as well. And then finally, just a quick preview, the OS dome sensor that I just spoke about on the last slide is a new sensor that we hadn't released before. So I'm going to give just a quick preview And we have another webinar specifically on that sensor because it's new and we want to kind of fully explain what the new product is and is capable of. And so I'm just going to finish with a quick preview of that. Sound good? Nobody can answer. So I think the answer is yes. So starting here, so I'm going to do a little bit of a quick review. Some people may have heard me or someone else at Ouster talking about this, but the core that powers our sensors is what we call our digital lidar architecture. This is unique in the lidar industry. We're the first company to take this approach. And what's key about this approach is that we have centered all of the architecture of our sensor on two small semiconductor components, a SPAD detector array and a VCSEL laser array. Prior to us creating these sensors, the typical architecture had individual components for each laser and each detector pair inside of the sensor. And the sort of big eureka moment for Angus and Mark, our two co-founders, when they started the company, was using this, at the time, relatively new technology, SPAD technology, to combine all of those individual laser and detector components into a single SPAD array and a single laser array. So rather than having individual components, we have one single monolithic SPAD that has 128 detectors embedded inside of it, rather than 128 separate components. So what that lets us do, our sensors pack 128 channels into an extremely small form factor. It's the smallest 128 channel sensor that you can buy on the market today. But more importantly, what this digital approach really allows us to do, it allows us to have tremendous improvements over time as semiconductors improve without having to change the core architecture of our sensor. So our sensors are going to look and function the same, but over time, as the technology, like the microscopic technology within the SPAD improves, our sensor performance is going to continue to improve over time. And what we're talking about today is exactly what that looks like, because the L3 chip that we just released is the first chip that really ups the performance in a way that we've been talking about and demonstrates the power of this digital approach. So just a quick refresher on what a SPAD detector is. I was just speaking about it. A SPAD detector is a single photon avalanche diode. It's a photosensitive piece of silicon. It's embedded on top of a processor. So what you're looking at here on the right, the SPAD array is the chunk in the middle. You can see our L2X, which is our prior generation chip, and our new L3 chip on the right. That section in the middle is the SPAD detectors. Outside on the right is where the basic low-level data processing first starts happening. So what a SPAD does that's relatively unique is, it's in the name, it's a single photon avalanche diode. So the way a SPAD works is it counts individual photons that are hitting each pixel. Our sensors have 128 channels. In camera terminology, you could call that 128 pixels. So the SPAD counts the raw number of photons hitting the pixel. So it's not measuring the strength of the light, it's directly measuring the quantity of photons hitting the SPAD and outputting that into the image processor. Now, I'm kind of previewing here where we're about to go, but for SPADs, one of the key metrics of performance is sensitivity. And the reason for that is something called signal to noise ratio. So we're going to talk just briefly about signal to noise ratio. We have a prior webinar talking about this, but I want to recap it because it's really important for understanding what's happening with the L3 chip. So signal to noise ratio, it's a common ratio used by LiDAR sensors. Obviously it's used generally in statistics, but the signal to noise ratio for LiDAR is very important because when you're firing out a laser and measuring the return back, at every laser wavelength, there will always be naturally occurring sunlight at that same wavelength. And in order to accurately know what photons came back from the laser pulse and what photons are coming from the natural environment, like the sunlight, you need to identify the signal from the noise. So the noise would be the sunlight, the signal would be the laser light, and you need to find a peak in what your light detector is measuring in order to determine what was the laser light, in order to determine how far away the object was that the laser hit. So a LiDAR sensor, a time of flight LiDAR sensor specifically, the way they work is they send out a laser pulse, they measure the amount of time that elapses, and then measure the pulse, measure photons coming back. So key is understanding when the pulse that you sent out comes back. That's key for determining how far away the object is that the laser light hit. So pulling out the laser light from the natural sunlight is key to making a LiDAR sensor work. Now, apologies, this is a bit of a busy slide, but it's a really important point. Signal to noise ratio is something that LiDAR sensors, LiDAR makers are constantly trying to improve. When you have a lower signal to noise ratio, it's much harder to determine which photons are coming from the laser of the LiDAR sensor and which are coming from the natural sunlight. And that uncertainty in determining which photons are from the laser and which are from the sunlight presents itself in the point cloud generated by the LiDAR sensor. When there's a lower signal to noise ratio, either some points can't be detected with certainty. So if the signal to noise ratio is bad enough, you won't get any point in the point cloud because the sensor will say, I can't tell if this is sunlight or if this is an object. So I'm not going to give any return at all. Or you could end up with a highly imprecise return where, say an object is 10 meters away, the light is bouncing back, but you have a very low signal to noise ratio. It's very hard to tell if that object is exactly 10 meters away or if it's 10.5 meters or 9.5 meters. And what happens in subsequent frames of the point cloud is you get points that move over the range significantly. So lower precision on a LiDAR sensor generally is a result of a worse signal to noise ratio. Between these two charts up top, you can see like a worse signal to noise ratio versus a better one. On the right, you can see clearly, even just visually as a human, how much easier it is to pick out the peak of photons coming back. Picking out that peak is how you determine what the laser light is vis-a-vis the sunlight. So when you have a higher signal to noise ratio, like you see in the chart on the right, it's much easier to pick out what laser light is coming back, which gives you more detection confidence that there definitely is an object there in the field of view of the LiDAR. And it gives you much more certainty in the exact range of that object. So you end up with better detection and you end up with higher precision as a result of a better signal to noise ratio. Causes of a poor signal to noise ratio, I didn't write this on the slide, but you might wonder what affects this. The two main drivers are going to be the intrinsic attributes of the LiDAR sensor itself. So sensors themselves having a stronger laser, having a better detector, both improve the signal to noise ratio. And then the external environment also affects the signal to noise ratio. So having higher sunlight, that will increase the base noise level. So a really bright sunny day, which does decrease LiDAR performance for all sensors. One other attribute here that may come up, also the intrinsic nature of the object that the photons are bouncing off of, so what the laser light is hitting out in the world, also affects signal to noise ratio, in that a bright object reflects many more photons. So you get a lot more photon light coming back to the sensor and a much higher peak, which makes it easier for the sensor to know that there's an object and where it is. For a really dark object, like a shiny black car, having those don't reflect very many photons back to the LiDAR sensor. So you end up with a lower signal peak, a lower signal to noise ratio and less detection confidence, and generally lower range on those types of objects. So one really interesting and highly important, I mean, this is the physics of how lidar sensors work. But when you increase the photosensitivity of a lidar detector, the signal, so the number of photons received back from the laser pulse, that increases linearly. But the amount of noise in the world that comes into the sensor does not increase linearly. That noise is a Poisson distribution, and that increases at a rate of 1 raised to the 1/2. So that distribution is exponential, but is less than a linear function. And so you'll see what that means as we increase the sensitivity of the L3 chip. But first, just a quick crash course. We're going to put all of this together in a second when we talk about the chip, but shifting gears a little bit to talking about chip physics. So talking specifically about the detector and SPADs, there are 2 types of illumination. And when we say illumination, it's two ways of architecting your SPAD detector in order to catch light coming back from the environment. This terminology is very common in the camera industries. So for those of you who are photographers, this likely is something that you already know. But there's a type of image sensor called a front side illuminated CMOS sensor. In our case, it's front side illuminated SPADs. Out in the world, they're the most common type of SPAD used. They're easier to manufacture, and this happened in cameras as well, where front side illuminated CMOS sensors were prolific in the world before backside illuminated sensors were invented. The way front side illuminated image sensors work is the photons enter through the top of the image detector. They pass through a light filter, and then the metal logic layer of that image sensor is placed above the diode. And the reason for that is because of the wafer manufacturing done at chip foundries. This process is easier to do. It's easier to put the metal layer on top of the diode than it is to put it under. And so having a metal layer, they're very small, but there are metal components that sit above the photodiode, the actual image detector, or the actual light detector. And those metal components reduce the amount of light that makes it to the diode itself. So front side illuminated sensors have a natural limit on how efficient they can get as a result of that metal layer that sits on top of the diode. Now, as happened with cameras and is now happening with LiDAR sensors, we're just starting to see the first backside illuminated SPADs. So backside illumination effectively is turning, I mean, it's called backside because it's putting the diode basically on the back of the silicon rather than the front. So this is sort of an upside down front side illuminated sensor. But what this does is it puts the diode directly on the top of the wafer so that there's no metal layer blocking light coming into the photodiode. Manufacturing a wafer in this way is hard, it's complex, and so it's just starting to enter out into the world today. Backside illuminated SPAD technology is new. BSI technology is not new itself. It's been in common use in the camera industry for quite a while because it produces better results than front side illuminated CMOS sensors. But SPAD sensors specifically, the supply chain has been seeing a huge influx of investment. It's been following a curve very similar to camera CMOS image sensors. Much of the investment is coming from SPAD sensor use in all sorts of applications, from medical imaging to, like, the iPhone uses SPAD imagers. So consumer electronics, there are many, many billions of dollars going into the SPAD supply chain development. And the introduction of backside illuminated SPADs is a result of all of that investment and demand from the world. But to our knowledge, BSI technology has never been used in a industrial grade lidar sensor before, or an automotive lidar sensor for that matter. So finally getting to the payoff. The big change with our L3 chip is shifting from a front side illuminated SPAD sensor to a backside illuminated SPAD image sensor. What we gain from switching that architecture is a 10x increase in light sensitivity. So where our L2X sensor was measuring 1 photon, our L3 sensor is measuring 10 photons. That big gain in image sensitivity has huge implications for our signal to noise ratio. So as I was talking about a couple slides ago, when you get a 10x gain in image sensor sensitivity, you get a linear increase in the signal, in the laser light captured by the image sensor. So we get a 10x increase in returns coming from the laser pulses in our sensor. But the noise, the ambient noise in the environment does not increase linearly. It increases at a rate of 1 to the 1/2. So where you get a 10x increase in signal, you only get a 3x increase in noise. So as a result, you end up with about a 300% increase in the signal to noise ratio, a dramatic improvement in the signal to noise ratio. And as a result, when I was talking about the importance of signal to noise ratio, the L3 chip then gets all the benefits of having a much higher signal to noise ratio than our prior chip generation. So the 2x increase in sensor detection range, along with precision and dark object detection, which we're going to go through. So I have some quick stats here on the L3 chip. We're really proud of this chip. It's the realization of our digital lidar approach. What we've been saying for years is that our chips are going to get better and the sensors are not going to change in form factor, that the sensor is going to dramatically improve in performance. The L3 chip is the first time where that is actually true. We're actually delivering on what we've been saying. The sensors are dramatically improving with virtually no change in the core architecture of the sensor. So there are tons of stats here on the chip itself, but the main takeaway is the dramatic improvement in sensor performance. So this is a chart that we've used. It's on our website. We've used it in many presentations, and I just want to highlight it because it holds true, and that's the silicon digital lidar approach. Over time, as our chips get better, our sensors are going to continue to improve in range and points per second. So total number of points, frame rate, any of that will all be improved as a result of our chip improvements. The L3 chip is really the first major step change since we've been in large scale production. And we're going to continue to do that over time. This is not the last one. There's plenty of more headroom for us to continue to improve these chips, and that's what you'll continue to see from us. So I hope you're all a little bit technically fried from that very intense deep dive into the chip and why the REV7 sensors have much better performance. But for the rest of the presentation, it's going to be a little bit more visual, walking through what all of these performance improvements actually result for the sensor. So first, as a start, so the 2x increase in range. So what you're seeing here is an OS1 sensor on a freeway. Our OS1 REV6 had a range of approximately 45 meters at 10%. The new REV7 OS1 has a range of 90 meters at a 10% reflectivity. And you can see that really clearly on the zoom out. This center ring here is 100 meters. You're seeing everything within 100 meters of the sensor. Perhaps like a more practical example rather than just a car driving on the freeway. What this means is you're going to be able to see dark objects and highly relevant objects like a pedestrian at much greater distances. So we took out the sensors and did some data collection just to demonstrate what that actually looks like in practical terms. So you have a pedestrian here. This was me. It looks hot, it was hot, but standing out on the track and getting some measurements. You can see with the REV6, you're getting about 2 points on the person, and most likely those points were coming from something a little bit more reflective than the dark clothing I was wearing, like potentially my shoes, my face, or my hat. So you're getting about 2 points with the REV6 sensor. With the REV7 sensor, you can see very clearly not just the body of the person here, but you can see the arms extended very clearly from the REV7 sensor. So the pedestrian detection, dark object detection like a tire, any relevant objects, you're going to get those out at much greater distances with the REV7. So moving into, so raw range is obviously a big improvement. We've been talking significantly about that, but we don't want to totally gloss over that. The higher signal to noise ratio extends the range of the sensor, it doubles it, but also within the prior range of our sensors, the performance is dramatically improved as a result of that higher signal to noise ratio across the entire, that gain in signal to noise ratio is across the entire range of the sensor. So when compared to a REV6 sensor, even at a distance that was within the range of a REV6, the REV7 data is cleaner and sees more than a REV6 sensor did. So an example here is looking at the corners of this building in San Francisco. What this is, I mean, with a higher signal to noise ratio, you end up with higher confidence points, which allows you to get cleaner edges. When I was talking about the confidence in how far away an object is, that higher confidence is what gets you cleaner corners on like the 90-degree corner of a building, for example. And you can see that in the top-down view comparison on the right. So what you're seeing here, these two points are actually the bottom part of this building, and then this main point on the bottom is the front edge of this building. You can see the curved corners here on the REV6. The REV6 still does perform well, but those curves are pushing the limit of what the REV6 sensors can do, or those corners are pushing the limit of the REV6 sensor's precision. With the increased signal to noise ratio of REV7, you get much sharper 90-degree corners on buildings, so especially relevant for things like mapping. Another way of demonstrating this same concept is on roadways. So something that we frequently discuss with customers, we test internally, it's highly visual, is looking at the smoothness of the lines on a road. So on a vehicle that's traveling on any sort of dark concrete. This angle, this is the same function as you were seeing on the corner of the building, but it's when you're getting a worse signal to noise ratio with a weaker detector, you end up with more variability in the range of your points. And so you end up with more squiggly lines like you see here on the left with the REV6 versus cleaner lines here on the right with the REV7. And finally, just this is a common standard test for a lidar sensor, but showing we had a 10% reflective wall at 5-meter distance, and just to demonstrate how good the precision can get on REV7, we have this visual here. Here's the front view of the target on the right, and then a top-down view on the bottom, showing the full width of the wall, which is 2.5 centimeters, is the full min to max variability of the measurements with a 0.5 centimeter standard deviation. So moving a little bit, and the difference here is a little bit nuanced, but moving into darker object detection. So where precision is going to be the variability between points, range is how far the sensor can see. We're going to give a few examples here of how well the sensor can see either really small, really dark, or in this case, really dark and small objects that are within the standard range of the sensor. In this case, it's thin wires over a street. So what we did is we took a drive down a public transit street in San Francisco. You can see the the bus line, like the electric connection for the bus lines here going up and down. We took a drive down that street with a REV6 and a REV7 and generated a SLAM map and clipped out the roadway below, just so you could clearly see the wires on the street. And so this is a side-to-side comparison of REV6 versus REV7 on the same street. And what you're seeing is the direct effect of that higher signal to noise ratio. So the wires are coming through much more cleanly. You see significant more detail, and you also see more crispness, even in the points that are coming through. So across like the power poles, for example, or the lines that the REV6 does see, they're thinner and crisper with the REV7 sensor. A similar example that I'll flip through, but is looking at thin objects. So in this case, they're metal, they're kind of metal wiry crates that were outside of a warehouse. Just demonstrating both between the white, some of them were white metal, some of them were black metal, but demonstrating the sensor's ability to see the detail in those crates and even pull out the detail of the dark black metal crates. So this was taken with an OS1 sensor. And then we generated the SLAM map using the onboard IMU on the sensor. And so final example here of dark object detection. This is the most standard test that we see our customers run. Black cars. Black cars are very common on the road. They're also notoriously extremely hard for lidar sensors to see. Between the REV6 and the REV7, again, with that higher signal to noise ratio, a practical result is you get significantly more points on a black car. In this case, it's a car that's at an angle to make it even harder to see, and at a distance of about 15 meters. The way the dynamics of this work is for a given range, the REV7 will get many more points on an object than REV6. It also means that the REV7 will be able to see that object farther. It'll get points out at a farther distance than prior REV6 or any other sensor with similar range to our REV6 sensors. Okay, so those were kind of all my visual performance examples. I'm going to wrap up the explanation, kind of the deep dive on the REV7 upgrades by talking briefly here about some of the upgraded internals. So not directly related to the point cloud performance itself, but we did make other improvements to our REV7 sensors just as a result of all of our learnings over the past 4 years. So for one, we updated the FPGA on the sensor, so the signal processor on the sensor. The main benefit of that, it won't be a direct benefit immediately in a REV7. What the upgraded FPGA does is it gives us more room for future upgrades. So as we continue to improve our firmware over time, we're going to be able to continue to deliver better and better upgrades and more features in the sensor as a result of the expanded power of this FPGA. We also added an automotive Ethernet option. So a standard Ethernet cable has 4 twisted pairs for passing data. Automotive Ethernet has a single twisted pair, so the cable is a little bit lighter, thinner, cheaper, but it's also like it doesn't go into a standard RJ45 Ethernet termination. So it does require a full, the system needs to be entirely on automotive Ethernet. But we do have that option. Please just note that the hardware is different. So like the physical sensor is different between a standard Ethernet and an automotive Ethernet sensor. So if you do want an automotive Ethernet sensor, when you're talking to our team, be sure to specify that you want that hardware because you will not be able to run automotive Ethernet on a standard base T sensor. And then finally, we have learned a whole lot about how our sensors work over the years, getting them out tested in the world. And pretty much with every release, we continue to refine the design inside to further improve the reliability and longevity of our sensors. And REV7 is no deviation from that. We're continuing to deliver reliability improvements with REV7. So finally, just a quick overview of the sensor lineup. All four sensor types are available in 64 or 128 vertical channels. So that's vertical lasers in the point cloud. You can see quickly here on the table, this presentation will be posted afterwards. So if you want to take a deeper look, you can replay it and pause here on the slide. But we, share the range and field of view metrics that I already spoke to at the beginning of the webinar. Great. So a quick summary before we get into Q&A. The big headline and the big change with our REV7 is the new L3 chip. It's the new SPAD system on chip, and that's what's driving a 10x increase in photosensitivity, which leads to a big increase in our signal to noise ratio, which leads to the big increase in range, precision, dark object detection. The REV7 sensors also feature all these mechanical improvements, like the upgraded processor for improved firmware over time, like automotive Ethernet, and with higher reliability. So with that, I'm just going to end with what I said I was going to end on, which is a quick preview of the OS Dome, our new sensor. We're really excited about this sensor. It opens up a whole bunch of new installation options for lidar. So these sensors, they are roughly the same size of our existing OS 0 and 1. So if any of you are customers and have an OS 0 or 1, you can imagine roughly how the approximate size of these sensors. The OS Dome will have a field of view that's the entire area of the dome that you see on the sensor. It's 180 degrees, but it's a full hemisphere field of view. So this is a sensor mounted on a ceiling looking down at our kitchen in our office in San Francisco. You can see people milling around here, but yeah, we're extremely excited about this sensor. We think it's going to be a great application, especially for small, or have some great applications, especially like small robots, indoor crowd monitoring or security applications, potentially blind spot monitoring on larger vehicles, all of the above. So I don't want to overlook, we also have a webinar dedicated to mapping. I covered some topics that are pretty relevant to mapping customers, discussing precision, but that's going to happen on the 15th. The Dome webinar that I just previewed is going to be on the 21st. So getting a little close to the holidays, but hope you can join. Both of these webinars will be recorded. So if anybody is off on vacation, please feel free to register and you'll get sent a copy of the recording anyway. And if you can't attend, you can watch it whenever you're back. The place to go watch webinars on demand, we have plenty of older webinars that cover a lot of these technical details in even greater depth than I did today. Those are available at ouster.com/resources/webinars. And I'd be remiss if I didn't give a final plug, which is for anybody going to CES, please come by our booth. I actually don't have our booth number handy, but I'll make sure in our thank you email or in an email follow-up afterwards, we'll include our booth information, and please come visit us and we'll have a lot of these sensors set up and running live at CES. So I blabbed for a long time and am going to look through this Q&A, but we're running somewhat close to time. So I'm going to try to get through as many questions as I can, but for questions that we don't get to, we will follow up over email and I'll make sure that you get an answer to your question. So perfect. So first question, so is the range consistent across the entire field of view or is that at horizontal? The sensor's range is, so the question is asking, is the range on like the beam at the top of the sensor or the beam at the bottom of the sensor same as the range at the beam at the middle of the sensor? The short answer is no. There is some range variation across the beams. When you move from the beams in the middle will be the strongest. The beams at the top and bottom will be a little bit weaker, and that's just a result of the attenuation from bending the beams at that angle. The range degradation is not that significant though. I can double check and get an exact number on that, but the range drops I believe somewhere around 5 to 10%. So I know some sensors have significant drop off around the edges of the sensor. Ours are designed to minimize that as much as possible. Let's see. Is sunrise, sunset worse for a perpendicular mounted LiDAR versus noontime? Since sunrise, sunset will have the sunlight shining perpendicular directly into the LiDAR receiver. The answer is it honestly depends a little bit. What you'll get with direct sun is you can get a little bit of interference if the sensor is looking directly at the sun, because the sunlight obviously is extremely strong coming from the sun itself. So you will see a little bit of noise directly around the sun. But generally speaking, at noontime, when the sun is highest in the sky and the light is generally brightest in the world, you'll see a greater effect on the signal to noise ratio, where at sunset or sunrise, generally the signal to noise ratio will be higher, with the exception of the portion of the point cloud that's looking directly at the sun. I hope that answered that question. Let's see. So can you talk a bit about inspection use cases for thin, small features, specifically power line inspections? So I'm not sure exactly what detail we're looking for here. I did give the example of line inspection. I can say we have a number of customers using drones or handheld or car mapping, using our sensors for power line inspection. The improved small object detection of the REV7 sensors makes them a really powerful option for especially increasing the scan time, because you won't have to get as close to some small objects in order to scan them cleanly. And so the REV7 sensors, they're small, they're light, they play well on drones. They're only about 450 grams. And so we do have a number of customers using those sensors for that use case. But I'm not sure exactly what the question was there, so I may have to follow up. And second question, is there a change in beam divergence for REV6 and REV7? The answer is no. The beam divergence is exactly the same. The sensor architecture, aside from the change in the chip, is the system architecture is the same. So the optics generally have not changed at all, and the beam divergence stays the same. And one question just to clarify, by 128 channels, you mean the equivalent of 128 scanning laser planes. What is the angular resolution between consecutive points in the scan? I'm going to make this my last question because we're running up on time. So yes, with 128 channels, we do mean 128 horizontal planes, scan planes. So that is correct. The question on angular resolution between the consecutive points in the scan, I used to have this memorized. So our sensor is configurable. You can set that resolution to either, so you can set it so that it's 512 points in a circle, 1024 points per circle, or 2048 points per circle or per rotation. So 360 degrees divided by 2048. So it's either 0.17 degrees between the points for 2048 points in the circle, 0.35 degrees between points for 1024, or 0.7 degrees between the points in 512 mode. So that's configurable. It allows you, with the denser points, it does increase your data rate. And so there's a little bit of a trade-off there, but we make that configurable to allow you to customize it for what you need. Great. With that, I hope I provided some useful information and some explanation of what's so great about our new REV7 sensors. Please, if you have any questions, don't hesitate to reach out. And if your question wasn't answered, don't worry. We have a list here and we'll make sure we follow up. Thank you everyone very much for joining, and we hope to see you on another Ouster webinar. Thanks.